listen, so I get these requests about, they're concerned about the grade and all these things. I've had probably 5 or 6 so far in the last week or so. This is my advice. Now, I can't tell people what to do. So if you look at the amount of grade out, right? You know, what's final exam is what, 40%? I forgot exactly, isn't that right? If you look at that, look at the quizzes. There's a replacement quiz, and by the way, I'll write this out. Apparently, there are people that either didn't hear me or didn't understand. So what happens with the quizzes is, there's a quiz at the end, probably the last day of class. That quiz grade will replace your lowest quiz grade. The logical question is what if that is my lowest quiz grade? Then it's thrown out. Follow me on this one? So if it is your lowest quiz grade, I don't use it. If you missed a quiz, the number of quizzes added up are the same for everybody. Hopefully, we don't have 2 people missing, or 2 quizzes out. But that's a special thing. So if you miss a quiz, that quiz and all the other ones you have will be used together, all right? In other words, that will replace your missed quiz. Do y'all follow me on this? I'm trying to be as clear as I can about this. There is nothing about the final grade replacing anybody's quiz grade. I don't know where somebody sent me that. I don't know where they got that. If you missed a test, not a quiz, but the test, then you need a university-approved excuse, and you have to get that through Janet Moore at the dean's office. How many know who Dr. Moore is, Janet Moore? That's who you got to see. Don't see me. You got to get her to okay, in fact, that you have a university-approved excuse. I'm trying to be as clear about this so there's absolutely no misinformation out there. Now, so that's basically the way it works with the quizzes, the replacement quiz, whatever you want to call it. Now, how many quizzes are left? Another good question. We're having one Friday, then we're having one at the end of next week. That's 2. Y'all hear me? Then at the end, I think it's the 6th. Isn't that the last day of class? The 6th is a Friday, if I'm not mistaken. Then you'll have your replacement quiz. Do y'all hear me on this one? Write the good news or whatever you want to do. That means 3 quizzes are still outstanding, is what I'm trying to convey to you people. Now, you can do math better than I can with an Excel spreadsheet. You know the percentages and all this. So you can figure out where you stand in the class. Now, on Canvas, does not allow me to put in the scaled grade. Well, it could, but you would get more confused. The way that thing works, it doesn't allow me much freedom. I can't take my Excel spreadsheet and just upload it. It doesn't work that way. Even though you think it does, it doesn't. So you know the scaling on the test. Everybody follow me on this class? You can do math better than I can do math probably when it comes to your grade. You're more serious about that. You can figure out where you stand, guesstimate, or you could actually solve for what you need to get if you're talking about that. Now, and here comes another question that I get. It's not the same words, but it's the same real curiosity. Is the final exam and the final grade going to be curved? The final exam, I have no idea. It hasn't been created or given. I don't have any idea what's going to happen on it. Generally speaking, the final exam is a reflection of your basic knowledge of the entire semester. All right? It is comprehensive. It is closed book, closed notes. However, on that exam, I get the largest number of perfect scores. I'm going to tell you this. If you look at the quizzes, look at the tests, they will reflect one thing: homework problems. I promise you, there is not a single quiz, not a single homework problem that doesn't, or quiz or test problem that doesn't come directly from a homework problem. Yes, I changed the values. I may change one resistor into 2. Do y'all follow me? But it's the same template. And if you want to challenge me on it, I can show you any problem and how it changed. Now, an inductor may change to a capacitor or something like that. But you got me on this one. Follow me? Now, people that are serious, this is my own impressions. Everybody here is smart. You're not at this point in your career just by dumb luck. You're smart people. If you get serious, Even if you had a bad score on the second test, you probably can do very well. I mean, you probably can get a C, maybe. I mean, if you got an absolute 0 on everything, all right, drop. I don't think there's anybody here, but I mean, you know, we're talking about extremes here. But if you are going to spend the time, and you can spend the time, some people can't, they work, some people are, you know, in athletics, some, who knows, but the band, anything like that. If you don't believe you have the time to spend, then you probably should drop. But if you're committed, if you want, I mean, you're going to get through this, I believe in myself, I can do it. I mean, there's some people that are actually just skating. They're way over the top. I mean, and I understand it. It happens in every class I've ever done. But there are people that are probably going to get A's, but they're nervous. And I mean, that makes sense to me. I was a little angsty too when I was sitting where you were, because I never knew how much more work was going to be required, or exactly what's coming at you. You could get sick, you know, everything. But I would take confidence in the fact, if you've gotten this far, you've got the abilities, if you just commit to it, you'll do okay. You're going to be fine. I can't promise you what grade you're going to get, but you're not going to fail. Now, here's who fails, in my opinion. Don't ask me for absolute proof on this, but this is my opinion. People that, oh, I'm going to get by. I'll worry about that the day before the final, maybe 2 days before we'll have a study session. Boy, that's a dangerous way to live. I tell you, not only in this class, but in life in general. You do that, you're probably going to end up wishing you didn't at some point. Just remember what I'm saying. I'm trying to give you some practical advice. I mean, if you don't know something now, maybe you had a terrible time with Thevenin, learn it. Or, I don't know, RC or RL transient circuits. Whatever you don't feel comfortable on, now is the time to learn. You got an entire week over Thanksgiving to take care of stuff you don't get. Now, it's not just my class, but that's my advice for all your classes. Tons of MEs in here. I know you got thermo, 1 or 2, probably some other ridiculously tough courses. That would be my advice to you on those courses also. But don't be foolish. And one last thing I'll say, if you are one of these people, you're doing well, and I'll just skate the final and stuff like that, that's 40% of your grade. Don't do that. Don't give it up. I mean, I don't know what else I can say. Clear enough on this, guys? Now, final exam, I haven't given it. So then the last question I said, well, what if my average is 68.3%? Will I get a D? Probably not. But don't ask me direct questions like that when I haven't even given the exam. I mean, if the average is 105 on it, I mean, I can say probably you will. But what I'm really trying to tell you is your grade will be a reflection of where you stand in the class as a whole. In general, 70 and above, right? You're going to get a C or better, right? 80 and above, 90 and above. But there may be some adjustments at the end when everything's said and done. So I cannot say anything more about that. Please don't continually send me questions that are just weird. You know, what if I make this on this and this and this? You got an Excel spreadsheet? Take a look, see what happens. I don't know. All right, fair enough. Any other questions about grades? Because I have been getting them. Man, I got questions about this. Oh, one last thing. Now, I want to state this clearly. You cannot use your phone on an exam. Got that? You cannot use wearable electronics on an exam. If you get more time or you have a special need, something like that, see me. I prefer to have people in class here. If you need extra time, I'll give it to you after the exam in a conference room. But what I'm not going to do is deal with the whole about, well, what if this? What if my calculator, you know, the battery fails? What do I do? Don't worry about that, all right? Try to get your calculator charged up and make sure everything's working, and quit being like a paranoid schizophrenic nut, asking stuff that makes no sense to me. I mean, I frankly don't know what to tell people like that because I'm not a therapist, but there's something wrong. What if I get a flat tire? I don't know. I mean, you're going to the extremes. Okay, what was your question?
Does that replacement quiz is going to be on what we learned that week?
Yes, it always is. I will never ask you stuff unique to you about something you missed before. All right? It's going to be on the current material. Follow me? Now, are there any questions about, I hope that settles it once and for all. I'm getting really tired of this stuff coming out. Anything else? I hope I made myself clear. I don't know what to tell you about studying if I don't have enough time to study, other than if you really mean that, drop it. I mean, I can't, yes.
You mentioned at the beginning of the semester us potentially having a dropped quiz grade. Is the replacement quiz in place of that? Or is that going to be on top of that
If
replacement
you
grade?
never miss the quiz, that quiz that you take again will replace your lowest quiz grade. If you miss the quiz with an excuse, it replaces that quiz.
Okay.
So the total number of quiz scores that people will be averaged on are the same. Got that? Can I be clear? All right? All right. All right. I hope I'm clear. All right. Now questions. Did you have another question? If it's about that phone stuff, you're not going to use your phone as a calculator. I'm going to tell you that right now. Oh, I've used it before. Great. You can use it in whatever class lets you, not this one. I don't know if you have to, I don't know if other classes are like this, but I have very unique questions in this class. I don't think I've ever been asked those type of things. All right, anything else? Now, how about the homework? Do you have questions about the homework? I figured at least there'd be some curiosities about some of these problems because you have not done it. I hope you're keeping up with it. Anything? Sydney? Amanda, nice to have you back. You made it. Anybody else? How about you guys back there? Nobody? Nothing? How many tried when you asked that? All right. Did you have any questions? I mean,
10:30.
hold on. Now, I'm going to level with you. The filter problems are a little bit different because I didn't have much time to really get into them, and I will do one or two. So this is 10:30. Is that right?
Yes, sir.
Okay. Okay, 10:30 is a good problem for everybody, for a lot of reasons. So, for this problem, question is something about closed loop gain that I didn't spell out. If you did the reading, you got it. Here, they're going to have some voltage going in to the input of the op amp. Well, actually, it's going to go through 2K. And then they'll have a parallel combination of a resistor and a capacitor here. This is 12K, and this value of C is 10 microfarad. And they say sketch the magnitude of the closed loop gain and label the critical value. Now, I'm going to level with you about this. This is a great problem for a lot of reasons. It showcases the real idea behind filtering and how you would use op amps to accomplish certain filter characteristics. This is a high-pass filter, or I should say a low-pass filter, sorry, low-pass. So the way I always do this, think of this circuit right in the template I'm giving you here. If you have something with some Z1, we're in the frequency domain here, and this is negative, positive, and you can crown that here, and you have a Z2 here. Now, this should be Z2. When I look at that circuit right there, by this time probably a lot of you can see this. This is an inverting output, and the output is going to be minus Z2 over Z1 times the input. I'm going to ask a question. I'll prove this in a second. How many realize that? Just by looking. All right. Now, if you've done these problems, you've been keeping up, this should be pretty recognizable. That's what it's going to be. To prove it, we'll just do this. If there's an input voltage, that's 0 volts, that's 0 volts. Do you agree with that, first of all, everybody? Can you also, how many see this right here? I'm trying to be very clear, but I need to know something about, if you understand it. Everybody down here see it? You with me? If that's 0 volts, we know the current here, right? That current would be equal to Vn over Z1. Do you all agree with that? Right? I mean, this is obvious, but if you have any question, now's the time to throw that question up at me. All right, that means none of the current can go in the negative terminal, right? That's an absolute no, right? Can't. Has to flow this way. So it has to flow that way, which means this voltage right here, and I'll just call it V2, would be equal to this current times Z2, or it's going to be equal to Vn times Z2 over Z1. Does everybody follow me on this? Can you all see it in the back? Far back guy? Over here? All right, now if you can see that, the output voltage should be clear. V out here, I always say start from the negative terminal. That's 0, that's 0. You can see this is a voltage decrease of that V2 value. You all see this? So V out here is going to be minus Vn times Z2, I'll get out of your way, Z1. Does everybody see that? It doesn't matter what Z1 and Z2 are. It really doesn't. But you have to at least understand the concepts. Everybody with me? Making sure. All right. So the closed loop gain is really the gain of the circuit with the components, which means in this case, and I'm just going to say this, they symbolize this as a voltage gain, AV, and that's V out over Vn, which would be minus Z2 over Z1. Can everybody follow me on this? If you can, let me see your hands. I want to make sure. Y'all with me on that? That's called the closed loop gain right there. It's the voltage gain. All right, so that's it. Can you all see it? With me? All right. Now, if you look at that, you can see that negative sign. You all with me? When they plot this, they will plot magnitude of the voltage gain versus frequency. They really don't care about that negative sign because they're assuming the input is going to be a sinusoid of some sort, which means it has negative and positive parts of the waveform of equal magnitude. So y'all follow me? So they're assuming a constant frequency, and they'll change the frequency of the input. Follow me on this, class? This is not something with a square wave and stuff like this. They're going to just change the frequency on a sine or cosine generator. So what they normally do is this, and I'm going to erase this circuit. Well, I'll erase this circuit and I'll show you. This is always done. In your classes, I'm sure you see this type of plot done. It's going to be logarithmic on the horizontal axis, logarithmic on the vertical axis. And so they'll show you this. This will be, and I can do it with F or omega. I'm going to use, well, I'll use F first, but a lot of times it can be omega. So what they're going to do is show you the magnitude, and this will really be like 20 times the log typically. It doesn't have to be this, but of AV. It could be AV, but typically it's that. Now you don't, I'll explain this as I go. And then on this axis, this is the actual plot here is going to be proportional to the log of F. What you're going to do is get like this. So this could be like 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. Y'all follow me? That's just logarithmic on both axes. Y'all with me, class? Now, when they plot this, and I'll get to that one, what you'll see is something like this. And these are called Bode plots. I'm very curious about this. How many know what a Bode plot is? What class did you have in it, if you don't mind me asking?
Aerospace systems.
It should be in a systems course. Doesn't matter if it's aerospace, electrical, mechanical, whatever. How many have had some form of signals and systems course with Laplace transforms and all that? Doesn't everybody have to take that? I thought MEs do too, don't you? What's that? I had to take that when I was a sophomore, I think, because it was used everywhere. I think Laplace transforms, didn't you have that in math department? I mean, before you even got into engineering, you had to take Fourier transforms, Laplace transforms, all that. Isn't that right? I mean, you've seen this stuff. This is just an extension of really a Laplace analysis in the frequency domain. S is really sigma plus j omega, sigma is real. Anyway, not going to spend that. So it's going to look like this. Pay attention to this part. This is typical of almost every circuit you're going to get, with one exception. So it'll look like this. These are straight lines. This would be a Bode plot. Now, really, it would look something like this. But what they do, they don't show the curve here. They're going to show a straight line. It's going to go straight and down. Y'all follow me? That's a Bode plot. It's going to be straight line approximations of a curve. I want you to listen to the next point I'm going to make, and then we're going to do this problem in its entirety. In the reading, they discuss this. But right here, this frequency right here, I call it a break frequency. It's really termed a 3 dB frequency. What that really means is the input, if this is flat, if AV is flat, now I'll basically say if the magnitude is unchanging up to a certain point, and then it drops by 1 over square root of 2 of that magnitude, it's called a 3 dB point. So right here, you can make a little note, and we'll talk about this. This is called the 3 dB point, or you could call it the break frequency, and it is the value where AV, right, at this point, will be 1 over the square root of 2 AV maximum. And I'll apply this, and that's that frequency. But you're going to see it's almost always very clear. You can see it in a heartbeat when you do the analysis, and I'll show you how. If you haven't done this problem, please be attentive. You with me so far? At least the ideas. All right? Now, for our circuit right there. Erase this, and we're going to do the analysis. That may be a lot more complicated than you need to worry about. For right here, remember I said AV for my circuit, which will be a function of frequency. I'm going to put it as a function of omega first. Is going to be minus Z2 over Z1. You all follow me? I'm just putting it down as we found it a second ago. Now I'm going to go ahead and just get rid of that negative and talk about magnitude. Okay? Next, I'm going to identify the values of Z1 and Z2. For this circuit here, Z1 is this. So Z1 is simply 2K ohms. Is everybody with me on this? Now the way you write the next impedance becomes a bit important because it makes the analysis easier. A lot of times what people do is take this impedance, and by the way, this, we're just going to call this R for now, right here. I'll call it R2. And I'll call this C, just C. But the impedance of C right here is 1 over J omega C. Does everybody agree with that? How many understand that point? The impedance of an inductor and a capacitor, you must know it past this course. You'll see it on the final exam. All right, capacitors, 1 over J omega C, inductors, J omega L. Everybody got that? in the frequency domain. So now, when I get this impedance, there are two ways. This would be my Z2 right here. There are two ways to get it. Now please listen. I could take this impedance R times 1 over j omega c, right, plus R plus 1 over j omega c. You all hear me? That's one way, but you'll have some complexity because you see that j omega c term in the numerator and denominator. The recommended way that I tell you, if you ever see two of these things in parallel, to say that Z2 is really 1 over the first impedance plus 1 over the second. Y'all follow me? I'll write it down, just mention this. A lot of times people don't see it. So it's 1 over the value of R, the parallel combination, plus j omega c. Right? Because it's 1 over the impedance. 1 over R is 1 over R. 1 over j omega c is just j omega c. How many see this? Most of you probably see this, and I don't mean to bore you, but I have to be clear about this. Now, the way you want this, I'm going to multiply top and bottom by R. Y'all hear me? When I do that, I get this. I get R over 1 plus j omega R times C. Y'all follow me? Far back, guys? Everybody? All right, now that's the way you want it. Now, when I look at this closed loop gain, it's Z2 over Z1. I didn't put R2 here, but this would really be R2. So it's equal to R2 over 1 plus j omega R2C, and it's divided by 1 over R, right? And really 1 over R1. So what I'm going to do is just put R2 over R1 here and show you what I'm talking about. Can everybody follow me what I did and why I did it? I'm trying to rip out all the constants and put them in front. Then things that will vary with frequency become apparent. How many see what I've done? Can you all follow me on this one back there, guys? What don't you see? Just ask me.
So, multiply by R on top of R.
Yeah, first over here, this is R2. All right? So when I take, first you see how I got this? Multiply both sides, top and bottom, numerator and denominator by R2. You get R2, 1 plus j omega c R2. That's this. That is my Z2. Now, the output voltage gain magnitude is Z2 over Z1. That was Z2. R2 was inside. I pulled it out because I want R2 over R1 to be a constant in front of there. Y'all with me, class? How many see what I've done? With me? As far back, I mean, you guys, credit to your eyes. You should do a commercial for whatever you're doing to keep your eyes up. Because I don't know how you see it. Anyway, now we plot this. Here, I'll plot versus omega first. Now listen. So if I was to plot that versus omega, and we call it log of omega on this, I'm going to make it real easy. Log of omega, and we won't even bother with the log in the vertical axis, but it's got to be a magnitude. You with me? Now listen. If it's a magnitude of this, I'm going to magnitude here, then what I need to do, I can take the R2 over R1 out in front, and then I have to have a 1 on top, but then I have to square both of these terms and take the square root. Now the R2, by the way. Can you follow me on this one? The reason I have to do the square root is because it's complex. I have a real and imaginary part. To get the magnitude of that, I have to square the real part, and I have to square the imaginary part and add them together and take the square root. You do not square the J term. You'll get -1. Do you all hear me on this? How many understand that? Over here, you guys got it? All right. Now, if we do that and plotted it log of omega on this axis versus just magnitude of AV of omega, I'm not even going to put down anything more than that, not the log. What do you notice? What happens when omega is 0 here? Class? It's just R2 over R1, as if the capacitor wasn't there. Do you all follow me? In fact, the capacitor looks like an open circuit until its impedance is about equal to that resistance R2. You all follow me? So if you're plotting this, just going out here, you keep going, it'd be flat, but there would be one particular frequency where all of a sudden things start changing. Here's where you pay attention. Do you see how you have one here? Well, when all of a sudden omega RC, omega R2C is equal to 1, that's when that thing becomes important and it'll start dominating. You all follow me, class? And it will start going down. This point right here, the way you figure out what that point is, you say omega R2C is equal to 1, which means omega is equal to 1 over R2C, so that frequency there would be 1 over, if you follow me, R2C. That would be this frequency. And I'm going to call it omega 3 dB. So if it was versus omega, that's where it would happen. Now please hear me on this part. This is going to be very similar to things you see in your other engineering courses. It's almost an overlay. Normally what they do is they put 20 log of the magnitude of anything that has to do with force or pressure or anything like that. Whatever it would be on this axis. Here it's voltage gain, but it doesn't matter. And they will plot it versus the log of whatever the functional form is. It could be temperature, it could be frequency, if it has to do with some sort of a stress, whatever. What you're going to see is it's going to start. This is the point where this term starts getting large here, and it's going to start bringing it down. This will start coming down at a rate of minus 20 dB per decade, which means every decade of frequency, this particular thing will come down by a factor of 10. 1/10. You all follow me? And I'm not going to get into math on that. I'm just going to, how many have seen something like this in your courses? Is that aerospace thing you took to? Are you both aerospace right there? A mechanical? What course in mechanical?
Systems, system dynamics.
Oh, the class that you're going to get next semester. I see. All right. Now, I'm not going to ask you for this plot out here. What I'm going to ask you, if I ask you something, it'll be for this frequency and some estimate of a sketch. It's coming down there. Y'all with me? Now, please listen to this next part. Usually, it's not omega. Go ahead, ask the question. Now is the time, buddy. You sure? If you can't read my writing, if there's any question about why I'm doing what I'm doing, ask it. What I'm trying to do is figure out how this thing's going to vary as a function of frequency. And I see right here, it starts coming down. Now, I'm not going to ask the specific question, but a term used is what is the gain bandwidth product. The bandwidth would be the frequency range where there's no appreciable change in the gain, or the gain is the voltage gain. Follow me? Then it starts going down. So the bandwidth would be from here to the 3 dB frequency if it was an omega. Well, I'm going to change that in a second. The gain bandwidth product that you probably are going to hear something about this at some point in your careers is really going to be the amplitude here, AV, times the frequency W3dB. And you're going to find out one thing. I mean, you're not going to be required to know this for the exams or for the quizzes. But that product is a constant for that operational amplifier right there in the circuitry. So if I change the values of the capacitor for that topology, I can move this point way out here, but I'll I'll decrease the voltage gain. Y'all follow? I can keep moving it out, but that area under that rectangle, it goes AV times W 3dB will be a constant. That's the one takeaway from this. At least put it in the back of your mind, because you're probably going to see some of this stuff for your filters. You guys have to have laboratory work where you do filtering, don't you? I mean, at some point, maybe is anybody here a senior? Senior, have you had all your labs or no? You have? Did you get anything where you designed a filter? High frequency filter for anything?
We did a little bit of stuff in MATLAB for.
Yes, MATLAB is the key. They're going to use MATLAB essentially for everything, unless you got a very young professor that wants Python. Or Octave. Octave is, by the way, for everybody's sake, Octave is the free version of MATLAB. I don't know if they tell you, how many know what Octave is? Oh gosh, you don't have to buy MATLAB. You can use Octave, it does everything. You guys know that or not? No? Spelled as it is, OC Octave. It's free, you can download it, it's wonderful. I use it. Python's free. Do you know what Python is? It's basically, it's an add-on. I'm going to use one of the two of those things all the time. Anyway, back to this thing. We're going to analyze that circuit, but I want you to listen to me. It's not normally shown with omega, it's usually F, all right? What's the relationship between F and omega? Class? 2 pi, right? 2 pi F, which means this frequency would be omega 3 dB over 2 pi, and here's the kicker. That frequency would be the 3 dB frequency, F3 dB, this is the one they're looking for, is going to be that frequency over 2 pi, and that would be F3 dB, or the cut frequency, and right here that would be F3 dB. So now we go back to that problem with this. Y'all with me, class? If we can forget about the logarithmic stuff for a second, this gain right here, that gain right there in magnitude is R2 over R1. Let's look over here. R2 is 12K, that's 2K, that would be 6. Does everybody follow me? How many can see that? Right? You guys can see it, can't you? Or not? You get it? All right, so it's R2 over R1 is 6. So this value, AV equals 6 here. It's going to be 6 until I hit the frequency where omega RC is 1, and that frequency is F is 1 over 2 pi RC. So this frequency is going to be 1 over 2 pi R2, not R1, R1, R2C. Can you tell me what that is? So it's 1 over 2 pi, I hope I'm not out of time. 2 pi, R is 12, K, that's 10 microfarads, 10 to the minus 5th times K is 10 to the 3rd, 10 to the minus 2, 12 times 10 to the minus 2. So what is that frequency? Can somebody tell me? You asked the question, can you just tell me, sir? Or whoever has a calculator. Just tell me.
It's like 1.33.
Say again?
1.33.
Anybody confirm or deny that? 1.33? Hertz, not radians per second. Is that what they have in the book as a solution, or the solution? Huh? Yes? No? I mean, I was assuming you guys had some of that stuff up, but no?
Yeah, yeah, right.
4.32.
Okay,
Close.
all right. I messed up. Y'all with me, class? Now, the logical thing, if you're thinking rationally, is, am I expected to know that? The answer is yes, but here's what you're expected to know. The bottom line. How to get this. So, if, you know, as diabolic as I am, if I put another resistor here, you should be able to see those two are in parallel and reduce the complexity. Y'all follow me on this? They're not trick problems. They're just seeing if you have maintained some information from before about parallel. I promise you, what I'm doing here, I'll be yelled at if I did that. You never did that. Well, now you do. All right, they're in parallel, all right? Something even worse that I might do is this, that's really bad. Another resistor there, right? Got me? Don't kid yourself. I'm telling you, pal. I have them march up to my office and yell at me, we've never seen that. Y'all follow me on this one? Those are in series. Just reduce it to one series value. Yes, I would put them in parallel too. Go ahead.
For that graph on the right over there, at the F equals, at the 3dB.
The break frequency, yeah.
AV isn't actually equal to 6, right? It's some not.
It is the point, and if you want the truth, it's exactly 1 over the square root of 2, what it was at 0.
So 6 divided by the square root.
Yeah, but don't worry about that. All right, that's the point where it starts going down 20 dB per decade. I'm going to say you would have to know how to analyze a circuit like that based on the Z2 over Z1. Follow me? Now, Z2 and Z1, who knows? I could put a capacitor here, right? How dare you? If I put a capacitor here, what changes? Now over here, right? Basically here, I would have a 1 over j omega c, possibly plus r. Or it could be just 1 over j omega c. Y'all follow me on this one, class? 1 over j omega c is the capacitive reactance, all right? If you had a series resistor, it's r plus 1 over j omega c. This is not, I hate to say rocket science, because some of you guys are rocket scientists, but I mean, do y'all follow me? So that is the template. And I'm gonna just be fair about it. If I put a capacitor and a resistor here, it's called a high pass filter, because at 0, when omega 0, you get no output of the voltage. So I'm just leveling it. So what might I do? I'll probably give you a low pass filter if I'm asking about it. Write it down. Oh, low pass filter. That means capacitor, Z2. All right, I'm trying to level with you guys. I'm not trying to make this hard, but you should be somewhat interested in this because you're probably going to use it. Now, something else I'm going to say about this. I gave you problems, and I'm running out of time. I give you problems with waveforms from waveforms in the input that are time varying. Y'all follow me? They were either differentiators or integrators. Do y'all remember that? Those are still legitimate problems for Friday. However, from the bottom of my heart, and I haven't made it out, that kind of stuff is far more important. Y'all with me on this one? Than integrators and differentiators. How many know you can do integration and differentiation on MATLAB in real time with anything, symbolic, or you can actually take measured data and do it. All right, it's easier to do it that way. But that right there, that amplifier circuit I'm showing you, that is useful in real world. I'm leveling with you. Some of you will probably have to use this in your laboratory work. Has anybody used op amps here? Somebody said. Anybody you have in your lab? Anybody else? Anybody use PLC? Programmable logic controllers? You have? I'm just curious what's out there. I know you made pinball machines from, did you tell me that? Somebody told me that. Right? I mean, you do also, I don't know how you make them, by the way, but I'm guessing. So, out of fairness, and for the sake of time, I'm going to do, do you have another one you want me to do, or I'm going to just pick one? All right, I'll pick one. How about 1035? Got me on this one? We'll do it kind of quick. All right, as a class, work with me on this one because I think it would be beneficial to everybody. Now the capacitor's on the input. It could be on the input. It won't matter. Here the values don't matter. I'm going to call it R2 is 10 k ohms. Here R1 is going to be equal to 1 k. And the capacitor is 1 microfarad. I'm gonna tell you, this is a high pass filter. Just capacitor in series with that, well, let's all see what it is. Maybe, I don't wanna say too much. But if we're gonna look at this one, that's a capacitor, that's a resistor. I'm calling that R1, that's R2. By inspection, what is Z2? Can you tell me? Can everybody see it's R2, right? I'm just gonna call it R2. You good with that? What is Z1? And I better put it down with the voltage gain as I'm at. By inspection, the voltage gain for this one in magnitude is going to be Z, I'll just put down Z2 over Z1. I want just the magnitude. I don't have a lot of time. You with me, everyone? All right. So now what's Z1? It would be R1, right, plus 1 over J omega C. Does everybody see that? How many do? I want to make sure I'm not missing somebody. In the back there, you guys with me on this one? The capacitive reactance is 1 over J omega C1 for this. Now when you go ahead and divide them, you get your voltage gain equal to Z2, or R2, over R1 plus J omega C. Can everybody see that okay?
Wouldn't it be one over J omega C?
I mean, 1 over, sorry. You're sorry. I'm trying to get this through too fast. Absolutely right, and I thank you. That was not an intentional mistake. With me? Maybe that's a mistake you might make. Y'all follow me, class? Now, the next thing I'm going to do is multiply top and bottom by omega C in this class. All right, J omega C. Follow me? The reason is, I'm going to have just one by itself. So I'm going to multiply top and bottom by J omega C, and I get J omega R2 over, and this is going to be 1 plus J omega, and this is going to be R1C. Now at that point, either this form or this form would be the correct closed loop voltage gain for that circuit. Y'all hear me? Now did you have a question? Okay. Now when you look at this, the next thing is the closed loop gain. This is actually a bandpass. Just let me say this. You evaluate this function at omega equals 0. By putting omega equals 0 there, what do you see AV is? Anyone? 0, isn't it? Omega's up top, that's 0. There's still a 1 down there. Y'all follow me? Now take a look at this. At some point, right, this thing's ramping at 20 dB. It's ramping proportional to omega here. It keeps on going up linear, even from 0. Do y'all follow me? This one down here's got a value of 1. So I'm going to tell you, and this is a little more complicated than you're probably going to be responsible for, but if you were plotting that, if this is versus omega and call it log of omega here, versus this AV, we're just going to leave it as AV magnitude for now. It starts at 0, but it's ramping up here, so it'd be linear. Keeps going, right? Because what? You see how this right here, this 1 will dominate. Y'all follow me? So get rid of that. But there's going to come a point where this will dominate that. So when omega R1C is equal to 1, then this will be of the same order as that, and it'll be flat. Y'all hear me on this one? Just listen. So it's going to go flat. That frequency right here is when omega R1C is equal to 1, or omega is 1 over R1C. R1C, pardon. Now, hear me and let me finish. You can figure this out because at that frequency right here, you can see that voltage gain will just be R2 over R1. The omegas will cancel. Take it going up. Now this is a high pass filter anyway. This is called a high pass. Does everybody follow me on this one? Now I'm not going to go there right now, but if you put another capacitor here, this would be a band pass. Then it would start coming down at some point. I'm not going to require you to do that. One thing, let me finish my thought here. One thing I'm going to require is a form of the closed loop voltage gain for any of these, and the 3 dB frequency for that first circuit or for this one. Y'all follow me in this class? Now, I've given you plenty of problems with plenty of examples, so please do this for Friday. And I can't telegraph this thing any more than I have already. Go ahead, question. Yes?
You said that was an iPass, you had a class here on C1.
Well, now, see, yeah, but the problem is it's in series here. Just listen, if it was in parallel, it may be different. You all right? So you have to go through the analysis. Just don't memorize it. Just, what if it was this way? What if these two were in series? Right? It's different. I can't say there. I hope I'm clear about this.